Namely, numerics is heavily based on floating point numbers, often as specific as the IEEE floating point numbers. And this has, on the one hand, had a tremendous boost to accelerated and fostered many applications of numerics. And nowadays, numerics is a common tool to many parts of science. But on the other hand, it has created a kind of blind spot to the disadvantages of floating point numbers. Sometimes it feels like Stockholm syndrome, because everybody is so stuck with it that people believe they are actually loving it. And to demonstrate some of the aspects of this blind spot, to exhibit this blind spot, I've quoted some results about rigorous computability and uncomputability of continuous data, which seems to contradict or surprise, or which people in numerics seem generally unaware of. And the first such result is Ernst Becker's construction of a computable function, even a C-infinity function, very smooth function, which mathematically, therefore, must attain its minimum on a compact domain, right? And in fact, this function attains its minimum in many points. The minimum turns out to be actually the value, it turns out to be 0. But on any point where it attains its minimum is a non-computable point. So this means that it is impossible to rigorously compute the sometimes so-called function argmin. So to compute the value, the minimum value, that's 0, but the argument or any argument of many where this function attains its minimum, it is fundamentally impossible. And that's maybe a good justification for why popular numerical libraries such as the NHA library are very vague about the specification when they provide such an operation to compute a minimum argument to a given function, because it is, at least in general, and even smoothness does not help, it is fundamentally impossible. And such impossibility, cases of impossibility seem to have evaded the consideration in numerics, and so that's where we want to open the eyes to and put a rigorous foundation to numerics. Right, and you may argue that this is function of Ernst Becker is a very artificial function, and admittedly it is, but unless there's a definition of what is a non-artificial function, then it's still not a fully specified problem to say compute the minimum argument to a non-artificial function. That's exactly the question what that is. The second example that I quoted is concerned with partial differential equations. Numerical solutions to partial differential equations is a huge topic for the past 20 years. And if you enter partial differential equation in a popular numerical system or library, it will happily output some so-called approximations to the solution, but it will not in general say much about approximation in which sense and with what quality. And in general, it cannot, right? As has been demonstrated by this, again, admittedly artificial, but still mathematically valid construction of a computable initial condition f to the wave equation, where the solution is provably and inherently not computable. And if you enter this problem into common numerical methods, they will happily output something, but well, the theorem, the mathematical theorem says that whatever it outputs, it cannot be a rigorous approximation to a solution. And there will be no warning to that. It will just output something, and it's up to the user to realize that this is maybe kind of garbage, right? Like the iterated sequence, which converges to 100 numerically, but to 6 mathematically, one of your homework assignments. And the next myth, numerical myth or impossibility result is quoted from Orevkov, who constructed a computable continuous function from the unit square to the unit square, which according to Brouwer's fixed point theory must have a fixed point, right? But his construction is such a way that this function has no computable fixed point. So again, any library that claims to compute fixed points in dimension 2 must be lying at least in the rigorous sense. And the final example is the semantics of the test for equality. Here, the situation is kind of the opposite. This is what numerical scientists like to point out, that it is, well, not impossible, but I think the terminology says discouraged or used with care, whatever that means in the rigorous mathematical sense. And a rigorous mathematical sense we will assign, we will exhibit in this lecture, namely a sense which avoids this kind of paradox that in this case even inequality is infeasible and therefore no comparison at all among real quantities. And the solution, we will offer two solutions to rigorous semantics, one being a partial semantics and one being a multivariate semantics. And in this way, supporting actually or disproving numerical impossibility myth, namely that it is impossible to test for inequality. So this is a kind of a repeating of the motivation of this lecture, and now let's move on to start with the first main chapter, namely a brief recap on classical, that means discrete, theory of computing. And right, so to recall the outline of this lecture, so this will be chapter 1, recalling the computability theory. Then in chapter 2, we will talk about real computability theory, that is computability theory of real numbers, of real functions, and of real operators. This was initiated actually by Alan Turing himself. And then in section 3, we will recall a real, we will call discrete complexity theory with P versus NP problem. And in chapter 4, we will study real complexity theory. So chapter 3, discrete complexity, chapter 4, real complexity. And in chapter 5, we will then proceed to more general spaces beyond the real numbers. So that's our perspective for this lecture, which you can also find on the lecture homepage. So let me now show the slides for chapter 1. Here we are. Right. Recap of discrete computability theory. So we will talk about computability and uncomputability. We will recall a brief proof that the halting problem is undecidable problem. We will recall the notions of semi-decidability and the notion of reductions as a means to compare undecidable problems and even to compare problems whose decidability is currently maybe unknown. And this will later lead to the, or has historically led to the notion of polynomial time reduction that led to the definition of this famous class NP. Then we will consider formal model of computation. So I make a point in this lecture and generally to avoid the Turing machine model and instead use the more practically relevant formalization of while programs with complexity considerations. We will recall the so-called SMN property, which is a computational counterpart to currying, to type conversion. And then we will talk about oracle computation, which was introduced by Alan Turing in his PhD thesis. But again, here in this lecture, we will avoid the Turing machines and instead consider an oracle version of while programs, which is just basically while programs being able to make subroutine function calls. And iterating that will lead to the arithmetic hierarchy. And the reason why we discuss all these things is because they are then later in the chapter 2 extended to from the discrete case to real numbers and real functions, where all these concepts will re-emerge and play a crucial role. So that's our plan for today. And so historical recap: in 1941, the first digital computer became operational, maybe more or less simultaneously, at least in both cases in 1941 in Germany with Konrad Zuse's living room, and in the United States, the Mark I computer in, I think, Princeton. And 5 years before that, 1936, Alan Turing already wondered what are the capabilities and the fundamental limitations of digital computers. 5 years before the first digital computer became operational, he already wondered and addressed these questions, formalized these questions, and answered these questions, all in this famous work that introduced what we now call the Turing machine. Although Turing, of course, modest person he was, never would have dared to give it his own name, right? And I like to emphasize this because this is a very good example of what science is about in computer science, maybe to think ahead of actual technology, in this case, at least 5 years ahead, and to guide actual technology, because it turns out that Konrad Zuse's machine was heavily influenced by the theoretical considerations of Alan Turing. So again, 5 years before Turing's work, Kurt Gödel, the Austrian mathematician, had proved that there exist arithmetical statements about natural numbers which are true, but cannot be proven to be true, in a sense that actually involved early computability theory, namely recursion theory, it was called at that time. And Turing kind of, well, he was aware of that, and later he picked another logician, Alonzo Church, as PhD advisor. But the very qualitative consideration already shows that such uncomputable problems must exist. So for the sake of formality, let us consider any subset of natural numbers to be a problem, maybe a decision problem, in the following sense: given a natural number, input that to your computer, let the computer tell me whether this number belongs to this set or not. Okay, that's in this way, every subset of natural number gives rise to a decision problem. And now let's count how many algorithms there are and compare that to how many such subsets there are. And it's easy to see that there, whatever notion of algorithm you can conceive, any algorithm should be a finite object, right? Finite sequence of bits, finite sequence of instructions from some alphabet. But anyway, any algorithm should be described by finite matters, much like a proof. Proof should be finitary proof. So there can be at most countably many proofs. There can be at most countably many algorithms, whatever precise notion you consider. On the other hand, by Cantor's diagonalization argument, it's easy to see and was well known long time ago that there are not countably many subsets of natural numbers, there are uncountably many. So there are many more subsets of natural numbers than thus simply by counting, by comparing the cardinalities, there must be decision problems, subsets of natural numbers to which there is no corresponding algorithm because, well, any algorithm can decide only one subset. So maybe more rigorously, one can assign to every algorithm a subset of natural numbers that it decides. But for cardinality reason, this mapping from algorithms to subsets can never be surjective. Right. And but this is very basic counting arguments. Turing's achievement was to more or less explicitly exhibit such a problem, not just say that there must be many undecidable problems, but explicitly exhibit such a problem. And this is turned out to be the halting problem, right? So what is the halting problem? The halting problem is the following question in formula decision problem. Given an algorithm A and given an input X to that algorithm, does that algorithm A terminate on that input? And that's a important, practically important question because, as you know, some algorithms may not terminate. They may run into an infinite loop that never terminates. And whether an algorithm runs into an infinite loop or not depends on what input that algorithm is executed on. So an algorithm may terminate on some input and may fail to terminate on another input. So this is a valid question with two kinds of inputs and yes, no answers, outputs. So this is a decision problem. And if you want to make it more formal, here the input is algorithm and input to the algorithm. And this both inputs are input to another algorithm, which is supposed to provide the answer to that question. So here it's easy to get confused with all the inputs and algorithms. There are two algorithms involved and two inputs involved. One is the input X to the algorithm A, but the algorithm A is again part of the input to the algorithm which is supposed to answer this question to thus solve and decide the halting problem. But this is not uncommon. For instance, a compiler is also an algorithm which receives as input another algorithm, namely the one which is supposed to compile, right? So this is nothing unusual. It's not as, by far not as artificial as it may seem superficially. So this is a famous halting problem. And one idea of solving this problem could be to consider a simulator interpreter. Why not just simulate the given algorithm A on the given input X? This is what any, like a Python, for instance, would do. But the thing is, if the algorithm A does not terminate on the input X, then the simulator interpreter will keep on simulating the algorithm A and will never provide an answer. But we do require for a decision problem that it always must provide an answer, a correct answer. So constructing using a simulator or interpreter is not a valid solution to the halting problem. And in fact, Turing proved between the lines of his paper, and which we will make more explicit here in these lectures, that there is no algorithm, no hypothetical algorithm B that solves the halting problem that always and always correctly gives the correct answer to this question that we've just discussed. So again, this is really a pinnacle of computer science with emphasis on science as opposed to electrical engineering, impossibility results. And how can we prove that there is no algorithm? That's an exceedingly strong statement if you think about it. To maybe tomorrow could be maybe one student of KAIST could come up with such an algorithm. Is that possible? No, it will not be possible. And that's the essence. You can save your effort. You can stop looking for such algorithms because there's never going to be one. And the proof is classical, logical, mathematical proof by contradiction. Namely, we suppose that such an algorithm exists, an algorithm B, right? And then we construct from that hypothesis a contradiction and therefore prove that there is no such algorithm, right? Okay, so how does the proof by contradiction work? We take the hypothetical algorithm, call it B, and convert that into another algorithm, and then analyze the other algorithm to arrive at a contradiction that such another algorithm with the behavior of such another algorithm is impossible. And therefore, the hypothetical algorithm B also cannot exist. So what properties of the algorithm B do we use? Algorithm B has two inputs, A, another algorithm, and X, input for that algorithm A. And it has two possible outputs. Plus means the algorithm A terminates on input X, and minus means algorithm A does not terminate on input X. But there's no third possibility. The algorithm B will always provide an answer. That's essential, as you recall. Otherwise, a simple simulator would be a solution to the halting problem, but it is not. Now we turn that algorithm B into an algorithm B prime, which uses P as a subroutine, namely algorithm B prime receives only one input, an algorithm A, and executes this hypothetical algorithm B as a subroutine on the input A, A, or put differently, it runs algorithm B on input algorithm A and replaces input X with algorithm A, or put differently, it determines whether the algorithm A terminates on input of algorithm A itself. And again, this superficially seems like something artificial and made up, but recall that, for instance, the GNU C compiler is usually constructed or built on a new system in this very way. So a new Linux system, unless it's a turnkey system, comes with a very basic compiler, C compiler, and then you download the source code of the GNU, powerful GNU optimizing C compiler, and compile that with the existing slow and non-optimizing and restricted C compiler, and thus obtain your first version of a GNU C compiler on your machine. But that's not what I'm aiming for, because this first executable version of the GNU C compiler on your machine is still not optimized, right? It has been compiled with the basic C compiler. So what happens next is the GNU C compiler recompiles its own source code a second time, now with all optimization turned on. So the GNU C compiler is executed with its own source code the second time. So, and this is a kind of a practical counterpart to what is happening here. So we execute the algorithm B with input A for the algorithm and input A for the input to that algorithm to see whether algorithm A on input A terminates or not. And if it does terminate, right, then algorithm B will give a positive answer, and our algorithm B prime will take that return value of the subroutine call and start deliberately enter an infinite loop. That's how we construct the algorithm B prime. Whereas if the subroutine to call to algorithm B returns minus, a negative answer, then our algorithm B prime is constructed in such a way that it just terminates. So the observation here is that if algorithm B, hypothetical algorithm B exists, then also the algorithm B prime will exist with this behavior. So if we now arrive at the contradiction that the algorithm B prime cannot exist, then also B cannot exist. And this is exactly what we're going to observe. Namely, we consider what happens if we run algorithm B prime on input B prime, right? Like what happens if we run the GNU-C compiler on input of the GNU-C compiler. Well, in this case, it will produce a optimized version of itself, an optimized executable. But what will happen in our hypothetical case here is, well, there are two possible outcomes, right? If algorithm B prime on input of B prime terminates, what does that mean? Algorithm B prime on input of B prime terminates, then by the very construction and specification of the subroutine B, it means that algorithm B prime on input B prime, right, terminates. So our algorithm, hypothetical algorithm B, must give a, right. So in this case, if algorithm B prime on input B prime terminates, then that means that our algorithm B, which tells whether algorithm B prime on input B prime terminates, must give a positive answer, in which our case, our algorithm B prime deliberately enters an infinite loop and does not terminate, which is, if you've paid attention, is a contradiction, because we're just considering the case where algorithm B prime on input B prime does terminate, and thus have arrived at the contradiction that in this case, it does deliberately enter an infinite loop and does not terminate. So this is a contradiction. In the first case, well, algorithm B prime on input B prime does terminate, and leaves the second possibility, namely that algorithm B prime on input B prime does not terminate. So what happens if algorithm B prime on input B prime does not terminate? In this case, by the specification of our hypothetical algorithm B, it must return a negative answer, minus, which by construction of our algorithm B prime, lead B prime to terminate, which is again a contradiction to the case we're currently considering, where algorithm B prime on input B prime does not terminate. And here we've just observed that it does. So in either of the two cases, we arrive at a contradiction similar to the, yeah, this is kind of like this one of these logical paradoxes, right? If I say all Germans lie, what does that mean, right? It's a similar contradiction here. So there's a contradiction, and the contradiction means there is no such algorithm B prime, and therefore there's also no such algorithm B with this property that it always and correctly answers the halting problem. Okay, so the message to take from here, apart from this nice logical consideration about a paradox turned into a computer science problem, is that there are indeed problems which are algorithmically unsolvable, and they are not artificial at all. They're the one essential problem of software engineering, namely software testing. It's fundamentally impossible to detect incorrect software. In many places it's possible, but not always. So that's the message to take from here. And later in chapter 2, we will use that to construct real numbers and to construct real functions, which are essentially, ultimately impossible to compute, and thus them open up, reveal a blind spot of numerics where possibly things are considered to be easy or difficult to compute, but fundamentally impossible. That's beyond the realm of consideration generally. Okay, so now let's gradually become more formal. What is a decision problem? We've considered the decision problem to be a subset of natural numbers, and the answer to a decision problem is always yes or no. or more general function problems or problems where the output is this discrete setting is a natural number. And so let's consider a function from natural numbers to natural numbers. And being computer scientists that we are, 0 is one of the natural numbers in our consideration. And we're going to consider partial functions, which means the function may be undefined for some natural number inputs. And to formalize consideration, we say that an algorithm, we will formalize algorithm on the next slide. For now, let's just formalize what it means to compute a function. It means that the algorithm receives a natural number as input, encoded in some way. With this will be another matter of content later, maybe in binary or whatever. So algorithm receives a natural number as argument and outputs the natural number as value, and it must terminate. This is a subtle point to which I will return later. Whereas for arguments that do not belong to the domain of definition of the function, the algorithm must not terminate. It must enter an infinite loop. So that's a requirement for computing a partial function. And now we can formalize what it means to decide a subset of natural numbers as a particular case of computing a function, namely of computing the total characteristic function, which has value 1 for arguments inside the set and value 0 for arguments outside of the set. So that's the notion of deciding a set. And semi-deciding, that's kind of like half of deciding, right? Therefore the notion. That means the algorithm must terminate on inputs that belong to the set, as in the notion of deciding a set. But it must not terminate on arguments that do not belong to the set. So here, the value returned by the algorithm in this notion is disregarded, but the important question is whether it terminates or not. And if it terminates, that must mean that the argument belongs to the set. If it does not terminate, then the argument must not belong to the set. So, and we will justify this notion in just a minute. But before, we'll need to consider yet another notion, namely to enumerate a set. And this is a notion that is inherent and intrinsic to the discrete setting. Namely, to enumerate a set means that an algorithm computes a total injective function on integers, on natural numbers, whose range coincides with the set. So that means when executing this algorithm on argument 0, on argument 1, on argument 2, and so on every possible natural number arguments, it will in each execution will produce a natural number as output, right? It's a total computation, and all the collected outputs together must exhaust precisely the subset L of natural numbers, nothing outside and nothing, it must not miss anything inside the set. So these are three formal notions of what it could mean to about decision problems, right? Subset of natural numbers as decision problems, as a particular case of function problems. And if we have more arguments, more than just one natural number for input, or more values, high dimensional values, several natural numbers as output, then they can be recoded, combined into a single argument or similar value using Gödel's pairing function, kind of like Hilbert's hotel. This is a bijective function from pairs of natural numbers to natural numbers. So in particular, any two codes of pairs of natural numbers, different natural numbers have different codes, different natural numbers as code in this sense. So it is possible to recover the original pair of natural numbers from the encoded value. Okay, so now we've seen about all these notions, and What is the practical relevance to that? Well, we're most likely interested in deciding a problem, because in deciding there's always an answer. Like for instance, given a natural number, is it a prime number or not? That's a typical decision problem. We want to know whether it's a natural number, whether it's a prime number or not. Whereas with semi-deciding, there may be cases where the algorithm gives no answers. There must be cases, namely whenever the argument does not belong to the set, then by the very definition, the algorithm must not produce an answer at all, which for the user is of course very unsatisfactory, because in this case, the user will never be sure that the argument does not belong to the set, because by the very definition, the algorithm will must never say anything, must never say no, must never terminate. So semi-deciding is, from a practical perspective, weaker, a notion where only positive answers can be relied on and negative answers will never actually occur. So, and enumerating, that's kind of like a dictionary approach where all elements are enumerated in some arbitrary order, right? Not necessarily in increasing or any other order. For instance, the halting problem that we had seen before, considered as a subset of natural numbers, namely encoding both the algorithm as a natural number, the algorithm considered as a binary code, right? Sequence of bits, or maybe sequence of ASCII characters, each encoded in binary. This is semi-decidable, right? Why is it semi-decidable? Well, the interpreter provides an algorithm which semi-decides the halting problem, simulating the given algorithm on the given input until it terminates. Well, this is exactly what it means to semi-decide. And if the algorithm A does not terminate on the given input X, then the simulator will never terminate, which again is precisely the requirement for semi-deciding a set. On the other hand, it is not decidable. This is precisely what we've observed, what our paradox argument by contradiction has revealed. So that this is an example, the halting problem is an example that separates, that shows that indeed deciding and semi-deciding are two different notions in general. And on the other hand, these notions are connected by the following theorem, whose proof we're going to skip here, since this is just a recap of discrete computability theory. Namely, first, every finite subset of natural numbers is decidable. There exists an algorithm which can decide that. Basically, the proof idea is to hard code the elements of this finite set into the algorithm. And because it's finite, we can hard code it in finite information into a finite algorithm. The second property is a closure property, namely a subset of natural numbers is decidable if and only if its complement is decidable. So decidability is closed under composition. Again, the proof is not difficult. Basically, it means to replace the algorithm deciding the set L by an algorithm that kind of flips the final answer of the previous algorithm and thus decides the complement. And the third item of the theorem says and justifies the notion of semi-decidability, namely a set is decidable if both the set and its complement are semi-decidable. So indeed, it's only half of the decision part. And if we have both halves, semi-decision for the set L and for its complement, then that amounts to deciding the original set. Okay, and here the proof is kind of interesting, so I'm going to sketch both directions. So if the set L is decidable, if we have an algorithm that decides the set L, then we're going to convert that into an algorithm that semi-decides the set L. And recall that for semi-deciding, it means that for arguments that belong to the set L, it must terminate, which the original algorithm already does because it even outputs 1 and terminates according to the definition. But for arguments which do not belong to the set L, semi-deciding means that the algorithm must not terminate, which the original algorithm deciding the set, it does terminate. So how can we kind of mend and repair for that? We can add another instruction to the original algorithm in such a way that if the original algorithm is about to output 0, right, and terminate, then we add an infinite loop in this case only, and thus force the algorithm to not terminate. So by simply amending the algorithm deciding the set L, we in our proof can convert it into an algorithm that only semi-decides L. And the same is similarly can be seen to make the complement of L semi-decidable. Now the interesting part of this proof is the other direction. Suppose both L and L prime are only semi-decidable. How can we obtain an algorithm that decides L? And maybe a naive idea is to run the algorithm that semi-decides L. And if that algorithm terminates, then our new algorithm will output 1. However, that algorithm semi-deciding L does not terminate, then our new algorithm is supposed to output 0, but it cannot because it never gets that far. And the same applies if we first run, execute, simulate as a subroutine the algorithm semi-deciding L's complement. If that terminates, then we know that the input does not belong to the set and can output 0. But if the argument belongs to the set, then our simulation will never get as far to output anything else. So the trick here we seem to have a kind of priority problem, right? Which algorithm of the two algorithms to execute first, and the solution is to execute them, to simulate them alternatingly. One step of the algorithm semi-deciding L, one step of the algorithm semi-deciding L prime complement, one second step of the algorithm simulating L, second step of the algorithm simulating L complement, and so on alternatingly. And as long as both algorithms keep running, if any of the two algorithms stop running, if any of the two algorithms terminate, then our new algorithm will look which of the two algorithms has terminated, and if it's the one semi-deciding L, then our new algorithm will output 1. And if it's the algorithm has terminated that it semi-decides L complement, then our new algorithm will output 0. And indeed, this is correct, because as you recall, the two algorithms semi-decide L and L prime. If either of them terminate, it means that the argument belongs to L, or the argument does not belong to L. So whenever our new algorithm terminates, it does output the correct answer. In this sense, our new algorithm is partially correct. But how about total correctness? To see total correctness, observe that indeed an argument either belongs to L or belongs to L prime, neither to both nor to none, and therefore precisely one of the two algorithms that we are currently simulating, the one semi-deciding L and the one semi-deciding L prime, precisely one of them will eventually terminate. There's no telling when or which one, but precisely one of them will eventually terminate, and thus our new algorithm that alternatingly simulates them alternatingly will also eventually terminate, and thus we have established total correctness. Okay, and the last item of the theorem relates semi-decidability to enumerability, namely a set of natural numbers is enumerable if and only if it is semi-decidable and infinite. Well, it has to be infinite, right? Because the very definition requires that it is an injective total function from natural numbers to natural numbers. So the range must always be infinite. And if it is infinite and semi-decidable, then it is enumerable and vice versa, according to the theorem. And this part of the proof I'm going to skip. Again, it's not hard, but what we've learned here is the proof technique of dovetailing, namely of alternating, simulating tool, or more generally, countably many algorithms in order to avoid one algorithm possibly not terminating. And we'll reuse that technique when we talk about real computability and real function computability. Okay, so that concludes our second part of the recap on discrete computability theory, namely the notions of decidability and weakened notions of decidability and their relations. And let's now move on to comparing decision problems of known or unknown decidability using the notion of a reduction that later is and was historically refined to polynomial time reduction. So to this end, let's recall the formalization of the halting problem as a subset of natural numbers and consider two more decision problems, namely the non-triviality problem. The non-triviality problem asks, given an algorithm, whether there exists an input for that algorithm to terminate, whereas for the halting problem, the input is fixed, is specified, and where we wonder whether the algorithm terminates on input X or not. And non-trivial algorithm is one which terminates for at least one input. If an algorithm terminates for no input at all, that's kind of a trivial algorithm, right? So that's another decision problem. And finally, let's consider the totality problem, where we're asked, given an algorithm where that terminates on all possible inputs. And observe that the totality problem is not the complement of the non-triviality problem, right? The complement of the non-triviality problem is whether an algorithm terminates on no possible input. The complement of the totality problem is whether there exists an input on which the algorithm fails to terminate. So it's an important, subtle but important distinction. So the question is now, which of these problems are decidable, which are undecidable, which are semi-decidable, which is equivalent to enumerable, so we don't need to refer to enumerable anymore. And popular technique of establishing decidability, semi-decidability, undecidability is by reduction, by reducing the problem to a problem whose decidability or undecidability has already been known. So formally, a reduction between two subsets of natural numbers is a total computable function. So here you can see an example of two decision problems. This is a rectangle refers or depicts all natural number, and L is a subset of that, right? And L prime is also a possibly different subset. And here's the complement of L, everything outside of this shape. And here's the complement of L prime, everything outside of this subset. And we consider a total function from natural numbers to natural numbers with a property that it maps positive instances of the first decision problem, right? This means it's a positive instance, maps that to positive instances of the second decision problem, and vice versa. So this is what this equivalence amounts to. If and only if the first problem has the first instance has a positive answer, then also the negative second instance must have a positive answer, and vice versa. And the reason for that notion is that, here's an example, right? We don't require the translation function f to be injective, nor, right? So here it violates injectivity, nor does it have to be surjective. It can miss some elements of the codomain. these natural numbers. But the reason or observation is that if the second decision problem is semi-decidable, then also the first problem is semi-decidable. And if the second problem is even decidable, then also this first problem is decidable. And the reason, the argument goes as follows. If the second problem is semi-decidable, then we can combine the algorithm that semi-decides that problem with an algorithm that computes a translation function. Recall that we have required that function to be computable, so there must be an algorithm computing it. And combining both algorithms gives rise to an algorithm which I'm not going to argue actually semi-decides the first decision problem. Why is that so? Well, let's suppose this algorithm is presented with an input x. And what the algorithm, remember, what it does is it first calculates, applies the translation function to arrive at an instance of the second decision problem. And by this very property, if the argument to the first decision problem, if the instance belongs to L, then also the translated instance will be a positive instance for the second decision problem. And if the instance for the first decision problem is a negative one, then also the image, the result of the translation will be a negative instance of the second decision problem. So having thus executed the first phase of our combined algorithm, the translation, now comes the second phase where the algorithm, the translated argument, is executed on the algorithm that semi-decides the second decision problem. So in this case, if the translated instance belongs to L prime, this second algorithm, and this also our new combined algorithm, will output yes, and well, it will terminate. And if the first argument did not was a negative instance, then also the translated instance will be a negative one, and therefore the second phase of the algorithm will not terminate, because that's the notion of semi-deciding. So indeed, if L is semi-decidable, we have a computable translation, and also L is semi-decidable. Similarly, it's easy to see, and I leave that for you as an exercise to confirm that if L prime is decidable, then also L is decidable, provided we have such a computable translation. And this observation justifies this notation as a relation. L is at most as hard to semi-decide or to decide as L prime. Whenever L prime is semi-decidable or decidable, then also L is semi-decidable or decidable. So this is justifies this notion. And to further justify this notion, what do we want from such a notion, from such a relation? Well, we want it to be a kind of a order relation. So we want it to be reflexive, which I leave for you to verify. We want it to be, and we want it to be transitive. We cannot expect it to be antisymmetric. Please verify that for yourself. Please consider why we cannot hope or expect for such a relation to be antisymmetric, but transitivity is something we want for structural reason, and indeed it is satisfied. And I would like to again to leave it to you to verify transitivity of that relation. Okay, so in this way, it is not hard to verify indeed that the halting problem can be reduced to the non-triviality problem. So what could be a good reduction function for that? So the argument to the reduction function will be what? It should translate arguments or instances for the halting problem, where consisting of a pair an algorithm A and input in an input X for A into an instance of the non-triviality problem, that is um, um, only an algorithm. Let's call it algorithm B. And such a reduction function could, for instance, take the algorithm A and the input X and combine and hard code the input X into a new algorithm B that now executes algorithm A on the fixed input X. And I leave it to you to verify that this indeed constitutes a reduction from halting to a non-triviality problem, and thus establish this relation. And in particular, as a consequence, it follows that also the non-triviality problem is undecidable based on the below consideration. So non-triviality is another undecidable problem, but it is semi-decidable, again using a dovetail search technique. Please verify that by yourself. And similarly, one can show that the halting problem is reducible to the totality problem, meaning that also the totality problem is undecidable. But right, the non-triviality problem is also reducible to the halting problem, thus establishing that also the non-triviality problem is at least semi-decidable, but the halting problem is not reducible to the complement of the halting problem. Why is it not reducible to the complement of the halting problem? Well, we've seen on the previous slide that since the halting problem is semi-decidable but undecidable, that means that the complement of the halting problem cannot be semi-decidable, because recall, if a problem is semi-decidable and its complement is also semi-decidable, then it must be decidable, which we know that the halting problem is not, and therefore it is impossible to reduce the halting problem to the complement of the halting problem, because that would establish that also the complement of the halting problem is semi-decidable. And furthermore, the complement of the halting problem can be shown reducible to the totality problem. Again, that's a nice exercise, but not vice versa. The totality problem is not reducible to the halting problem nor to the complement of the halting problem. And in this sense, the totality problem is strictly harder, is strictly more undecidable than the halting problem, whereas the non-triviality problem is as undecidable as the halting problem. Both are semi-decidable. So that means this notion of a reduction, of a computable reduction, allows to formalize and to formally compare different degrees of undecidability. And right here we've seen some instances of coinciding and the disagreeing degrees of undecidability. And right, as I kept pointing out, this is an original notion due to Alfred Tarski of a reduction, and later it has been refined complexity theoretically by Steve Cook and by Richard Karp, who arrived at the notion of a polynomial time reduction, which in turn underlies the definition of this complexity class NP. And in this lecture, we're going to, at the end of this lecture, we're going to similarly consider a reduction among continuous problems, which is important. It's called Weyrauch reduction because Klaus Weyrauch introduced it, but again, being the modest person that he is, he prefers to just call it continuous reduction. But the point is, of course, if we want to show some numerical problem to be hard, to be NP hard, then all these discrete notions are useless. They don't apply to continuous problems, right? And therefore, it was an important step in finding notions, finding definitions, right? That's I like to call the core or the highest level of mathematics, creating reasonable definition. I mean, everybody can come up with definitions, but definitions that persist, that's indeed excellent. And here we see such a definition due to Alfred Tarski, Steve Cooks, and Michael Rabin's definition of a polynomial time reduction, Klaus Weyrauch's definition of a continuous computable reduction, and Akitoshi Kawamura's definition of a polynomial time continuous reduction. These will be among the highlights of this lecture. Okay, enough promotion. Let's continue with basic facts and definitions. Maybe I'm not a big fan of Turing machines. They're important as underlying all notions, formal notions of an algorithm. But for pedagogical reasons, we're going to consider and rely on an equivalent, polynomial time equivalent, carefully constructed polynomial time equivalent notion of an algorithm that is arguably more relevant to practice and therefore more easy to digest, and that's while programs. So we'll introduce while programs syntactically, and then their semantics, not necessarily rigorously, because you will, that's the whole point, immediately understand the semantics, so we don't need to make it formal. So syntactically, assigning a value 0 to one of finitely many fixed variables, that's one instruction of a possible instruction of a while program. Initializing one of finitely many variables with 1 also is a permitted instruction. Adding two variables and assigning the result to another one, subtracting two variables and assigning the result to another one, dividing one variable by 2 with or with remainder, without remainder, whatever you prefer, maybe round down, is a permitted instruction. And the composition of two such basic or finitely many basic instruction is again a while program, and the instruction that gave rise to its name, a loop, namely a while loop, is again a while loop whose loop body is a while program and whose loop condition is a variable, is again or a loop program. And of course, for this loop to terminate, the loop body better modifies the variable, namely the semantics of the semantics of all these instructions is obvious. The semantics of this instruction subtraction is a little bit maybe subtle, because the content of the variables is restricted to natural numbers from 0 on, so no negative numbers, and therefore the semantics of this instruction of the subtraction is the following: that it is if the result is non-negative, then everything is fine, right? But if the result turns out or would be negative, then it is simply truncated and replaced by the number 0. So that's the semantics of the subtraction instruction. The semantics of the division by 2, as I just pointed out, is just round down to the, if the argument here is even, there's no point, but if it's odd, then please round down. And here's the semantics is while the value of this variable xi is non-zero, repeat this in loop, repeat executing the loop body, which is again a while program. So that means that the loop body better modify, maybe like decrement or divide by 2 or whatever, modify the loop variable xi, otherwise it will be an infinite loop, right? That's the whole point of the halting problem, detecting infinite loops. And so this is a very simple programming language, but it is Turing complete. It is able to simulate any Turing machine and vice versa. So that's why I prefer it for pedagogical reasons. And right here we see the semantics of the loop is executed as long as the loop variable, that should be an xi, loop variable xi, as long as this variable has value non-zero. and refrain from further formalizing all the other semantics. You already immediately, intuitively get it, right? So, and here, we need to encode algorithms. Remember, the halting problem involves encoding of algorithms, and here we fix some reasonable such encoding. For instance, encoding the instructions as a sequence of symbols in the popular ASCII alphabet, each one with its 8-bit binary code, and then combining all these bits, finite sequence of 8-bit blocks into one large natural number value. That's one possible way of encoding this. This is sometimes referred to as a Gödelization. And an important property is this UTM theorem, which says that we can do basically, we can simulate any given while program. So using this encoding, there's one fixed while program that can receive a code of a while program as natural number as one argument, and arguments or initial values of the variables of that while program, right? There are finitely many variables, and if we initialize these variables and then a natural number argument, then it can simulate the thus given while program on the given input. So that basically means that it's a universal while program. Technically, historically, this is called universal Turing machine theorem, but in our case, it would better be called universal while program theorem. And maybe the final, yeah, I think we've already exhausted our time. So let's postpone the SMN theorem and Oracle computation to the next week, and stop here with a recap. So we've talked about, here we are, we've talked about computability and uncomputability, the halting problem, semi-decidability, enumerability and decidability, reduction, and we've seen the while program as a model of computation that formalizes what it means for an algorithm to be an algorithm. And we've seen the UTM theorem and postponed talking about the SMN property, which is a computational version of currying, which we'll recall on next Tuesday. And the further perspective is to translate all these notions from the discrete setting of natural numbers to the setting of real numbers, to define and to study computability of real numbers. Again, the important part is first to find a good notion of real number computability, and actually we're going to find 3 notions of real number computability, and then be faced with a question to choose among them. But fortunately, it turns out we don't actually have to choose. And then we're going to study closure properties of real numbers, closure under addition, closure under subtraction, multiplication, and so on, kind of recreating the computability theory of natural numbers and natural number functions for the real case of real numbers and for real number functions.